Morning, everybody. Welcome back to Calculus Life Today. We got a quiz that's here today. Directional Derivative off the side. No homework. Any questions or comments before we get started for today? All right. In that case, go ahead and put everything away. It is quiz time. Go ahead and take a few seconds to finish up your thoughts. And pass your quizzes forward, please. Press your quizzes in, please. Alrighty. So it's going to be the last, standard 11 is going to be the last standard and what I would call kind of the second major unit of the course, which is kind of our unit on derivatives, differentiability, what are some basic things that you can do with the multivariable derivative. And this standard is going to be focused on properties of the gradient vector for some multivariable function. So to start out with, if we had a function f going from Rn to R, can anybody remind me what the gradient vector is going to be? So in other words, kind of what relationship does the gradient of f as a vector have to the original function f going from Rn to R? Preston? Yeah, it's going to be the vector who's made up of all the partial derivatives of f. So if f, for instance, is taking in n variables, say x1 to xn, and it's going to spit out some scalar expression, then the gradient of f evaluated at a point at x is just going to be partial derivative of f with respect to x1, partial derivative of f with respect to x2, partial derivative of f with respect to xn. And so back in standard 8, we talked about what this gradient is, just this vector of our first order partial derivatives. And we use the gradient to help us compute tangent planes, or tangent hyperplanes, if depending on if we're going from R2 to R or R something bigger to R. And this gradient vector, when we dotted it with the vector x minus a, was kind of what we helped use to actually find tangent planes to functions at given points. So this standard, we're going to be looking at two other applications of the gradient vector. In other words, two other things that the gradient vector can be used for. And the first of which is going to be the idea of taking a directional derivative of a function. So we're going to take a look here at a function. Function is going to be given by f of x comma y is e to the 2y times sine of x. If you want, we're going to write this down on the next page of the packet when we work through an example, so you don't necessarily have to write this down right away. We're going to be looking at a point A, which is given by pi over 3 comma 0. And here is a graph of said function. Don't really know how to describe the shape of this function, other than the fact that it's for values of y that are negative, it kind of looks like a flat plane, but for values of y that are positive, if x is positive, it shoots up really, really big in the positive xy direction. But if y is negative and x is negative, or if y is positive, excuse me, and x is negative, then it shoots downwards towards negative infinity. And in particular, we're going to be looking at the graph of this function at this point here. This is kind of our a value. The point on our graph where we have an x-coordinate of pi over 3, a y-coordinate of 0, and the z-coordinate of square root of 3 over 2. That's just what we get if we were to plug in a here into the function f. If we were to plug in pi over 3 for x, 0 for y, it would spit out square root of 3 over 2 as our z-coordinate. This is going to be the graph that we're looking at. If we were to take our first order partial derivatives, del f del x and del f del x and del f del y, we would be taking the slope along kind of these two directions, where the positive x direction here is going to be going out this way, so to the right, as we look at the graph from this angle. If we were to take del f del x here, for this function at this point, that's something we talked about how to do in Standard 8. We differentiate treating x as a variable, y as a constant, then we plug in our point. But just from looking at the graph of this function, does it look like when we travel in the positive x direction, meaning off to the right here, does it look like we're going to have a positive slope or a negative slope at that point? Meaning if we were traveling kind of along this red line to the right, are we going to be moving upwards? Is it going to be an uphill climb traveling in that direction at that point, or is it going to be a downhill climb? Okay.
Right at the point, it looks like it's a positive slope.
Yeah, it looks like it has a positive slope here. If we were to go out this way further, it would start having a negative slope. But at this point right here, it looks like to me that our partial derivative del f del x is going to be positive. How about del f del y? Where del f del y is going to be taking the slope in the positive y direction, so sort of this way. So if we were to sort of go up the slope this way, are we going to be getting a positive del f del y or a negative del f del y? Meaning, is that going to be an uphill climb or a downhill climb? Yeah?
It's also going to be positive.
Yeah, it looks pretty positive. Looks like a pretty steep climb up the hill here if we were to travel in the direction of the positive y-axis. And would you estimate, just from looking at the graph, that del f del y is going to be bigger than del f del x or smaller than it?
I'd say bigger.
Why is that?
It looks like a steeper slope.
Yeah. There's both a positive slope in the x and in the positive x and in the positive y direction. But the slope going this way on the red line is small positive slope, whereas going up this way on the blue line is going to be a very positive slope. It's going to look super steep in that direction. So just from looking at this graph, I would estimate that del f del y is also going to be positive, and it's going to be more positive than del f del x. So that's stuff we talked about back in Standard 8, looking at the slope in the x direction, looking at the slope in the y direction. And if we wanted to, and eventually we will, we can actually find del f del x, del f del y at this point and kind of verify what we're kind of assuming just from looking at the graph. Problem is, though, there's other directions we could travel in other than towards the positive x and the positive y-axis. And in the other directions we could travel in, maybe we don't have a positive slope. So for instance, if we were standing at this point on our graph, and we were going to travel in the direction of this arrow right here, or this arrow, by the way, I'm going to call V, is pointing in the direction of 3 over square root of 10, negative 1 over square root of 10. If we were to travel in the direction of that arrow, starting at that point there, does it look like we're going to have an uphill slope or a downhill slope? Yeah, tell me your thoughts.
Downhill.
Downhill. A lot downhill or a little downhill?
Just a little.
Yeah, a little bit. So, if I were to guess, I would say that the slope traveling in the direction of this arrow is going to be a very slight downhill slope. The problem is, we can't just find that slope from taking a partial derivative. Because as far as first order partial derivatives go, there's only 2 of them for a function here from R2 to R. One with respect to x, and one with respect to y. And so what we're going to be doing in this standard is we're going to be answering the question we asked way back in standard 8. How can you find the slope of a function in directions other than just towards the positive x-axis or towards the positive y-axis? Because technically, if we're standing on this point on a surface, there's infinitely many directions we could be traveling in. And so we're going to be looking at how do you find the slope in directions other than the directions that del f, del x, and del f, del y are going to point to. And to do that, we're going to introduce a notion called the directional derivative. Where'd my notes go? Here's the scoop. If f is a function from Rn to R, and if v is any vector that's going to give us a direction to travel in, and something that's going to be important is that v has to be a unit vector for this form. Someone remind me, what does it mean to say that a vector in Rn is a unit vector?
It has a magnitude or length of 1.
Yeah, there's a length of 1. Meaning, if you were to take the dot product of v with itself and take the square root, you would get 1. So, if you have a function from Rn to R, and v is a unit vector, then we can say that the directional derivative of a function f in the direction of that vector v is going to be an expression that we define by d sub v of f of x, which is going to be a limit as h goes to 0 of f of x plus h times v minus f of x all divided by h. And this is going to be the directional derivative, where what the directional derivative is going to tell us is if we were to travel in the direction of the vector v, starting on a graph of that function, the directional derivative is going to tell us the slope in the direction of the vector v, if we're standing on the graph of our function. So directional derivative is going to give us a nice way to sort of generalize the idea of taking first order partial derivatives, and that if we take del f del x, that's going to tell us the slope if we were to travel just in the positive x direction. If we have del f del y, that tells us the slope if we travel in the positive y direction. But the directional derivative allows us to say what's the slope if we were to travel in any direction. You just have to pick a vector v corresponding to that direction, and that vector v has to have a length of 1. But if you have a unit vector that points in the direction you want to travel, then the directional derivative, this expression here, is going to give us the slope of the graph if we were to travel in the direction of v. And then typically you would plug in a specific point for x. You plug in some a and say, if we're standing at point A, traveling in the direction of v, it's the slope is going to be given by this expression. So as a quick little example, before we go on to looking at this function, if f is a function from R2 to R, and if, let's say, v is going to be the vector 1 comma 0, so I, if we wanted to write it as a standard basis vector. So if v is a unit vector, which it is, it has length 1, pointing in the direction of the positive x-axis, if we were to take the directional derivative in the direction of v, that would give us a limit as h goes to 0 of f of x comma y plus h times the vector 1 comma 0 minus f of xy all over h, which if we simplify a little bit, it's going to give us a limit as h goes to 0 of f of x plus h comma y, because x comma y plus h times 1 comma 0 is just going to be x plus h comma y, minus f of x comma y all divided by h. And does anybody recognize this expression? It's an expression we actually saw way back in Standard 8, this specific limit, as referring to what is the slope of our function f if we were to travel in the direction of 1 comma 0, i.e. in the direction of the positive x-axis. So what's another way to refer to the slope of a function if we were to travel towards the positive x-axis? That's bingo! This expression right here is actually just del f del x. Meaning, if we were to take the directional derivative in the direction specifically of the vector 1 comma 0, then the directional derivative just gives us the exact same thing as del f del x. And similarly, you could also say that if v is instead the vector 0 comma 1, meaning v now points towards the positive y-axis, what do you think the directional derivative would be if the direction vector we're choosing is in the direction of the positive y-axis? Meaning, we're looking at the slope of our surface in the direction of positive y-axis. Emily? Yeah, that's just by definition del f del y. So the moral of this is that this idea of taking a directional derivative is just a generalization of your partial derivatives. If you were to plug in 1, 0 or 0, 1, the directional derivative is just going to give us del f del x or del f del y. But the difference between the directional derivative and these partial derivatives is that the directional derivative, we could plug in any unit vector and travel in any direction corresponding to a unit vector. It doesn't just have to be towards the positive x-axis or the positive y-axis. So, if I were to write that down in words, we could say the directional derivative can tell us the slope in any direction, whereas del f del x and del f del y each only tell us the slope in a single direction. So directional derivative is just like a more powerful version of del f del x and del f del y in some way. That tells you slope in any direction rather than just the two fixed directions that we talked about way back in Standard 8. Any questions or comments so far? So if we go back for a second to looking at this graph we had earlier, we have our function f. I purposely graphed out all these vectors and such so that f is going to be the surface. F of xy is e to the 2y times sine of x. A is going to be our point. Pi over 3 comma 0 is just the x and y coordinates of this point right here. V is a direction vector, meaning it's going to be a vector that we're going to treat as a displacement vector that starts at A and points in the direction we want to travel. And so in this case, if we were to talk about what's the directional derivative of our function f of xy at the point A in the direction of V, what we would get is basically saying what's the slope starting at this point on our surface if we were to travel in that direction. So just slope in the direction of V. Which, if we really wanted to, we could find by going out and actually evaluating this limit here. But that doesn't sound particularly fun. In fact, that sounds kind of horrifying. Try and evaluate this limit by plugging in this function f, plugging in a here for x, and this is going to be our v. So fortunately for us, we're actually going to have a theorem that's going to make evaluating the directional derivative a lot easier than trying to use this limit. And the theorem is going to say, it's going to relate back to the gradient vector in that we can say if f from Rn to R is differentiable at A, and V is any unit vector in Rn, then what's going to have to be the case is that we can take the directional derivative of f at the point A in the direction of V. So the slope, if we were to start at the point A, walk along the surface of our function in the direction of vector V, we can find that by just taking the gradient of f evaluated at A and the dot product of that vector with the vector V. So in other words, if we were to take just the vector consisting of del f, del x1 of A, del f up through del f, del xn evaluated at A, and we took the dot product of that vector with the vector v, then that's going to tell us the slope of our function at the point A if we were to travel in the direction of v. It's the gradient of f at A dotted with vector. So let's see if we can evaluate that for this function here. And here I am going to be moving on to the second page. But before I start erasing definitions and such, any questions or comments so far? So let's do an example. We're going to look at the function that we were graphing on the screen a second ago. So our f of xy is e to the 2y times sine of x. The point A is going to be pi over 3 comma 0. That's the point we're plugging into the function to get a point on the surface of our graph. And the direction we're going to be traveling is in the direction of v equals 3 over root 10, comma, negative 1 over root 10. And our goal is going to be to find the directional derivative of f if we were to travel in the direction of v starting at A. First question. Is v our direction vector a unit vector? We'd like to be able to use this theorem, which says just take the dot product of v with the gradient of f at A. But if we want to do that, we first need to know, is our vector v the direction vector actually going to be a unit vector? Is there any way we could check that? Yeah, Lord. Yeah, we should be able to just take the magnitude of that v, take the dot product with it with itself, take the square root, see if we get 1. And if so, then it's a unit vector. If not, then we have problems. So first, we're going to check if v is a unit vector. Which to do that, we can just take the magnitude of v, which is going to be square root of x component squared, so 3 over square root of 10 quantity squared, plus y component squared, so negative 1 over square root of 10 quantity squared, which 3 over root 10 squared is just going to be 3 squared over root 10 squared, so 9/10. Negative 1 over square root of 10 squared is just going to give us 1/10. Neato burrito. Our vector v is in fact a unit vector because when we take square root of some of the components squared, which is the magnitude, it does come out to 1. So in other words, this vector v is kosher to use with this formula here. So, next thing I'd like to do is to be able to plug things in to this formula here. But before we're able to just start plugging things in, what's going to be some useful stuff to find first? In order to be able to just use this formula given the information we currently have. John, what might be something useful to find for our function f if we wanted to be able to plug in stuff into this expression?
We want to find partial derivatives.
Yeah,
Of f
sure.
of x, y.
Yeah, we're going to need to know what the gradient vector is at our point, and to know what the gradient vector is, we'll need to know our partial derivatives of f with respect to x and with respect to y. So if we do that, we can set that up. So we're going to take del f del x without plugging in a point just quite yet. Avery, what would we get if we took the partial derivative of this f of xy with respect to x? E to the 2y cosine x. I like it. E to the 2y is just a constant with respect to x, so it, as a constant multiple, it just gets tagged along for the ride. And differentiating constant times sine of x is just going to give us constant times cosine of x. Let's see. And now we could actually say at the point we care about, at pi over 3 comma 0, that's going to give us e to the 2 times 0 times cosine of pi over 3. Let's see, cosine of pi over 3, I'm pretty sure is a half. And e to the 0 is just 1. This will give us 1 times a half, which is a half. So that's going to be our partial derivative of f with respect to x at the point A that we care about. Holly, how about our partial derivative of f with respect to y? 2e to the 2y cosine x? For the function f over there?
The e to the 2y sine x. Oh, it's sine x, I'm sorry.
I was saying, yeah, sounds like you were trying to differentiate with respect to x and y there.
Sorry.
Yeah, differentiating f with respect to y, sine of x is just a constant multiple, so it gets brought along for the ride. And differentiating e to the 2y is going to be e to the 2y times the derivative of our exponent, 2y, which is 2. And so that'll give us 2e to the 2y sine of x. So del f del y at at the point pi over 3 comma 0 is going to give us 2 e to the 2 times 0 times sine of pi over 3, which I believe is going to be 2 times square root of 3 over 2, which is just going to give us square root of 3. Questions or comments about how we found the partial derivative? Alrighty, John, we found our partial derivatives. What would you like to do with them?
Put them into the gradient vector.
Cool. So if we do that, we take the gradient at pi over 3 comma 0. What vector is that going to be?
1/2 root 3.
And it's going to be del f del x at pi over 3 comma 0, comma, you know what, agenda? I've had enough of you. Get out of my way. It's going to be del f del x at pi over 3 comma 0, del f del y at pi over 3 comma 0, which is going to be the vector 1/2 comma square root of 3. So that's the vector telling us our slope in the x and the slope in the y direction at the point pi over 3 comma 0. And now, I think we're ready to evaluate our directional derivative. Meaning, if we're standing at pi over 3, 0, what's going to be the slope if we travel in the direction of this vector v here? So what should I be plugging in here? Like that.
Plug in the gradient dotted with the vector v.
Yeah, we're going to take our gradient vector. Let's just write it this way. We'll take the gradient of f at pi over 3 comma 0, dotted with our vector v, which is going to be 1/2 comma square root of 3, dotted with 3 over square root of 10, comma negative 1 over square root of 10. Dom, how do we take this dot product here?
It'll be 1/2 times 3 over the square root of 10 plus square root of 3 times negative 1 over square root of 10.
Sounds good to me. Just multiply the first two components, add that to the product of the second components. And I don't really want to simplify that. I'm just going to say I already plugged that into my calculator, and it came out to about negative 0.07. So it turns out, if we're standing hello, Chris. If we're standing on our f of xy at the point A here, where A is at pi over 3 comma 0, and if we're traveling in the direction of this arrow, let's see, Tim, I think you said that you look like a small downward slope. Well, we found the slope in that direction. It came out to negative 0.07-ish. Does that sound about right for what you were saying?
Yeah.
Yeah, I would say so. The slope of negative 0.07 says we have a very small slope that is negative, meaning if we were to travel in this direction, we're going to be walking downhill since it's negative, but only just a little bit downhill since it's pretty close to 0. Any questions or comments on what we did here? So honestly, everything that we did as part of this process is stuff I think you could have done in previous standards, other than knowing this formula. Because finding the gradient of f at a point, that's something we did back in standard 8. Taking dot products, that's something we did back in standard 2. checking whether or not a vector is a unit vector, that's also something we discussed way back in Standard 2. So kind of, none of the techniques we really used were new, but the idea of finding a slope in directions other than positive x-axis or positive y-axis using this formula, I think was kind of the new thing about this problem. Yeah. Questions or comments? Let's look at another example. So if we look at the bottom of the page, here is another function for us to consider. F of x, y, z equals x times y times z, which we're going to be looking at the point A equals negative 1, 0, 3. That's going to be our point. And the direction is going to be in the direction of v equals 0, negative 2, 1. And I'm interested in finding the slope of f at the point A in the direction of v. Wait, is this something I can graph? This function at this point, you think?
I think you could with a computer. It's x, y, z.
Can we graph this function from R3 to R on like top plot? Yes. All I see you shaking your head.
Because it's really like an R4, visualize that.
Yeah, I think the last one we could is a function from R2 to R. That gave us sort of a 3-dimensional graph. This would give us like a 4-dimensional graph. We'd have to set like W equal to some expression in terms of X, Y, and Z as a function from R3 to R. I don't think we can really do that very easily. We can still talk about the slope, we just can't draw a picture or have a computer graph this to help us kind of visualize this one. So, we want to find this directional derivative of f at A in the direction of V. Where do you think we should start? Tim?
See if v is a unit vector.
Cool. Is V a unit vector? Meaning, is this vector here, 0, negative 2, 1, going to be of length equal to 1? Sure?
No,
Why not?
doesn't matter.
It's not a unit vector. If we were to take the magnitude of V, we would get square root of, what, 0 squared plus negative 2 squared plus 1 squared, which is, it's going to come out to square root of 5, which is, I don't know, something a little bigger than 2. So, V is not a unit vector. Gadzooks. How do we get around that? It'd be nice if we were able to say, have a unit vector that still worked, but the vectors V that we were given telling us direction was not a unit vector.
Or we could just turn
Ooh, turn
it into one.
it into one. How do you propose we do that?
Divide by the magnitude.
It is indeed. Yeah, so what we can do here is our original vector V isn't going to work. So what we can do instead is we can find a unit vector that points in the same direction as V, which in standard 2 we said is just going to be the same as taking V divided by magnitude of V. So now we're going to find a unit vector in the same direction as V, which if we do that, we'll take 1 over magnitude of V times the vector V, which in this case is just going to be 1 over square root of 5. I already found the magnitude of V, the square root of 5. times the vector 0, negative 2, 1. And when we evaluate this out, I think we're going to get 0, comma, negative 2 over square root of 5, comma, 1 over square root of 5. And if you want, you could check that's actually is going to be a unit vector. And it's going to be parallel to the original vector v, since it's a positive scalar multiple of v. So this will give us a unit vector in the same direction as v. And so I think I agree with you, Sarah. I think that's going to be something we could use as our direction vector instead of the original vector v. Something that points in the same direction, but happens to also have a unit length, meaning having a length of 1, unlike the original v that the problem gave us. That's always something to check out, watch out for in these problems, is making sure that your direction vector has to be a unit vector in order for this to work. Bibbidi boo. Lindsay, what would be something that might be useful for us to find? Now that we have our direction vector that we can use, what should we find next, do you think? Yeah, we find gradient vector. It's kind of the other piece of what we're going to need to dot with our direction vector. So to do that, we're going to need del f del x, del f del y, and del f del z. Well, what would we get if we differentiated f with respect to x? With respect to y? And with respect to z? Sounds good to me. All of these are just constant multiple of x. Derivative with respect to x is just going to be that constant, which is yz. Ditto with our other partial derivatives. So if we were to take our gradient of f, evaluated at the point A, so negative 1, 0, 3, we're going to need del f del x at that point, del f del y at that point, and del f del z at the point negative 1, 0, 3. Alan, what would we get for our del f del x, del f del y, and del f del z if we plug in those negative 1, 0, and 3 in for x, y, and z?
0, negative 3, 0.
Let's see. If we were to plug in del f del x, well, the y coordinate 0, so that comes out to 0. Ditto with del f del z, the y coordinate 0, so it comes out to 0. And for del f del y, x times z is negative 1 times 3 is negative 3. So there's our gradient vector. So if we wanted to take the directional derivative of the function f at the point negative 1, 0, 3 in the direction of v, which two vectors are we going to need to dot together? Okay. Cool. So 0, negative 3, 0, and the 0, negative 2 over root 5 thing down there?
Yes.
Cool. We have to remember here, even though we're taking the directional derivative in the direction of v, we can't use v for that in our dot product because v wasn't a unit vector. That's why we needed to use this vector instead. This one's not so bad. We do the dot product. I think we're just going to come out to 6 over square root of 5. In theory, we could do the same process from Rn to R for any n. You just have to, for each n each time you make n bigger, you just have to take one more partial derivative for the gradient vector. Since we had a function from R3 to R, we had to take 3 partial derivatives. If I was feeling particularly sadistic, I could give you a function from R10 to R and said, find the directional derivative. Same basic process, you just have to, your gradient vector is going to have 10 components to it, which I wouldn't do to you because I don't want to grade that. But the procedure works the same way. The biggest thing, the easiest mistake I think to make on this is to not realize your direction vector needs to be a unit vector. If we had used the original vector v, it would have given us a scalar multiple of the correct answer, but it wouldn't have been the correct answer. We would have been basically saying our vector v is too big, our directional derivative is going to come out to an expression that's steeper than it actually is. Yeah, questions, comments, concerns? And you don't have to write this down. I want to go back for a second to the same graph I've been pulling up all class. One of these days I'm going to figure you out. So here's the function f of xy at the point, the original e to the 2y times sine of x at the point pi over 3, 0. Instead of looking at the directional derivative in the direction of 3 over square root of 10, negative 1 over square root of 10, we're going to look at the directional derivative in the direction of the gradient vector instead. So the gradient vector is going to point, here's where I need the software to help me out here. It's going to be pointing that direction. And this is just the direction, if we were to travel in the direction of the gradient vector. Looking at this graph, does anybody notice anything special about the gradient, about the slope in the direction of the gradient vector? In particular, what can we say about the slope if we were to travel in the direction of the gradient vector along this kind of black path, compared to the slope we could have gotten if we had traveled across any other path? Yeah?
It looks like the steepest possible slope.
It is. It does look like the steepest possible slope. The most, if we were feeling particularly masochists and like we want to do some hardcore mountain climbing, that's the steepest direction we could go, the most uphill we could possibly travel. And in fact, that's going to be a theorem for us on the next page. Now I'm on page 3 in the packet. Where it's going to turn out to be the case that the directional derivative for, let's say, for a function f going from Rn to R at a point A, first of all, the directional derivative dv of f of A is going to be maximized, meaning it's going to be its biggest when v points in the same direction as the gradient. So in other words, if you're standing on your function at a point and you want to know what's the steepest, most uphill direction that you can walk in, it's going to be in the direction that the gradient vector is going to be pointing. In this case, towards x equals a half, y equals square root of 3, because those are our partial derivatives. Del f del x was a half, del f del y was square root of 3 at that point.
So then the vector v would just be the unit vector of the gradient, essentially?
Yes, yeah, your direction vector would just be take the gradient vector, make it a unit vector by dividing by its magnitude. And it's going to turn out that we can say that in this case, what the directional derivative is going to come out to be is actually just going to be the magnitude of the gradient vector. I mean, if we were to take the directional derivative in this steepest possible direction, what the directional derivative is going to come out to, the steepest possible slope we could travel in, that slope is going to be equal to magnitude of gradient vector. And in a similar note, we can also talk about which direction can we travel in to make the directional derivative as negative as possible, or as small as possible. And the steepest downhill direction, it's going to turn out to be the case, will be in the exact opposite direction to the gradient. So the directional derivative, dv f of a, is going to be minimized. We're going to make it as downhill a slope as possible if v points in the opposite direction to the gradient vector, which is the same as saying in the same direction as the negative of the gradient vector. So if going in the same direction as the gradient vector gives you the most uphill slope you could possibly have, traveling in the opposite direction to the gradient vector is going to give you the biggest downhill slope, the most downhill direction you could possibly travel. And in that case, if that happens, the value that the directional derivative is going to come out to is just going to be the negative of the magnitude of the gradient vector. Meaning that's the most downhill slope you can find at that point. Whereas the positive magnitude of the gradient is going to be the most uphill slope. And just so you know, we are actually going to prove this one. We're actually going to go through and come up with an explanation for why is traveling in the same direction as the gradient going to give you the biggest possible slope. But we'll do that on Friday. So on Friday, we'll actually go through and prove this result, and then talk a little bit about how to find tangent planes to implicitly define curves. You all have a good rest of your day, and I will see you all on Friday.
Do you have any math jokes today?
Oh my gosh, the joke! What was the joke of the day? Oh yeah. I run back in and sit back down. Are monsters good at math? The answer is generally no, not unless you count Dracula. Thanks for reminding me. Sorry I forgot that earlier.